Hi everyone, so in this video I'm going to discuss what is k-means clustering and what is a simple algorithm to solve or to attempt to solve k-means clustering. So first with the problem statement, you have two inputs. The first input is your observations. So these observations are given as a set of vectors, n vectors let's say, that are d-dimensional. So they can be any dimension. And your other input is this parameter k. That k tells you the number of desired clusters. So for example, let's say you wanted to classify images of cats and dogs. Then you'd set k equals 2 and try to fit every image into that cluster. If k equals 3, let's say you want to classify cats, dogs, and walruses, for example. And your goal here is to output a partition with k elements of x1 through xn. And a partition is simply means that each xi for every data point belongs to one and only one element of that partition. So that's why this k is here. So if we want to write this as an optimization problem, this script pk is the set of all partitions with k elements here. So the p that we're going to output is the arg minimum of this objective function here. And this objective function says we're going to sum up for each cluster. We take each cluster into account. That's all that sum term is doing. This is the number of elements in each cluster. 1 over it to normalize it, and then this is the variance of each term in the cluster. So if they're super far away within the cluster, they probably shouldn't be part of the same cluster. If there's other points that are closer to it, we probably want to put points closer to it that are in the same cluster. And note that this is an NP-hard problem. So having a fast algorithm to get the exact solution is not currently known. So I'm going to go over Lloyd's algorithm, which is sometimes called naive k-means because it's a very simple algorithm and much faster algorithms do exist to approximate this. But just keep in mind it's NP-hard, so you're only getting approximate solutions. So let's say that this is our data, x1 through x8. And let's say I have an initial partitioning given below. So the superscript 0 here is referring to essentially the iteration number. So just to label this, I'm putting x1, x2, x5, and x6. So obviously the solution here should be to put x5 through x8 in one class, x1 through x4. But for the sake of argument to show you how the algorithm works, I'm going to split between the two to show you how this algorithm converges. So, and then similarly, there's only two classes, so that means everything else goes into the other class here. So the way that this algorithm works is given your partition, you find the centroid of that cluster. So in this case, you just go through the math. So the centroid is given as the mean location of all the points in the cluster. And if you sum these up for the purple class here, for P1, that point is 2, 1.5, given by this x here. And similarly, you do the same thing for the green class, and that's at 2, 2.5. Okay, and then your next step is to compute the distance of every point in your set x1 through x8 to each of those centroids. So you have 16 calculations here because you have 2 centroids and you have 8 points. And you are going to place those. Okay, so for example, you can see this visual. Oh gosh, sorry. You can see this visually here. Say between x5. right? So you're going to compute this distance. You're going to compute that. You're going to compute that. Let's call this D2. Let's call this D1. And you're going to say, well, D1 is less than D2. So place X5 into let's use green. X5 now is going to be a green point. Again, remembering that this superscript is the iteration number. So on the next iteration, it's going to flip. We're going to make this a green point. And that's basically all the algorithm does. So, for example, if you just go through this calculation here, if this is too fast, you can pause the video and do the calculation yourself. So this point x1 is at the origin, and I'm computing its distance to the purple centroid here and the green centroid, the purple centroid here and the green centroid here. So you have to do that calculation for each point. And if you go through the math, you see that for the distance to the purple X centroid, 6.25, and the green one is 10.25. 6.25 is less than 10.25, so we keep it in the purple classification. Similarly for X5, that's the actual calculation here. So its distance to the green centroid is 1.25, and its distance to the purple one is 3.25. 1.25 is less than 3.25. So here, originally X5 was in the purple class, but now we're switching it to the second class. And so at the very end, if you do all these calculations, it will turn out that our intuition is correct for this example. And on the second iteration, this gets flipped to green, this gets flipped to green. This gets flipped to purple. This gets flipped to purple. And then we still have to keep going. So notice that we flipped the points, so we haven't converged yet. So we have to keep going, and we do the same exact calculation. We find the centroid of each classification, but since the points have moved, this centroid changes. Okay, so then that point, those points are going to be, you can see this visually very easily now. That's going to be your new. So this moves, right, because we reclassified. And then this new centroid is here. And then clearly, right, if we look at like x7, that distance, that distance, that distance, that distance are much shorter than, that distance, right, straight line distance, even though I drew a curve here. So at that point, we see that on the second iteration, we get that everything in the purple class, nothing got flipped to green, nothing green got flipped to purple, and so we're done. We terminate. That is our termination condition. But note again that this is only an approximate solution because it's an NP-hard problem. In this case, I get the exact solution because this is very much a toy problem where you can almost eyeball the solution. So in review, what is k-means? The problem statement is given observations, given n observations of d-dimensional vectors, and the number of desired clusters k, that is the k-means, find a partition with k elements of that data. So it basically is a classification, putting n things into k classifications. Lloyd's algorithm computes, given an initial configuration, computes the centroid of each classification, then for each point in the domain, computes its distance to the centroids, and then places it in the class that minimizes the distance to the mean. And that is why this is called k-means clustering, is because the centroid or the mean of the cluster is essentially how you're making this decision